Today we will discuss about the linear magnification. We will discuss about magnification, right? Basically, we will discuss about linear magnification. Basically, it is the ratio between the size of image divided by the size of object, right? It's the ratio between these things. We know that, and the size of image is known as q and the size of object is known as p. So basically m is equal to q upon p, right? So this is a formula of magnification, which is basically linear magnification. Now if you talk about the real image, like what will be the magnification of a real image. So the magnification of the real image is m is equal to minus q upon p. Now you'll be wondering that why I have put here minus, because consider this is a principal axis, this is convex lens, and the object is placed over here. As you know, it will converge like this, right? And obviously it will form an image. So we know that this is a y-axis and this is minus y-axis and this is positive y-axis. So the image is inverted but in the negative y-axis, right? So that's why the image over here is negative. So the real image is basically negative, right? Now let us talk about the virtual image. Like the virtual image is basically positive, minus q upon p. Why? Because for example, here is a image and here is a lens, like we have discussed this in the compound microscope. Axis will diverge and it will also diverge, so they will meet at a point that will be apparent to be converging. So this is the positive axis, this is negative axis, and already we know that we take virtual image the negative, so negative plus negative is equal to positive. So that's why the virtual image is positive and it is plus q upon p. So basically there are three conditions for the magnification as well, like magnification will be greater than 1 and the size of the image will be greater than the size of the object, right? This is the condition for this, and this magnification will be less than 1 when the condition will be like the size of object will be greater than the size of image, right? And m will be equal to 1 when the size of q, like the size of the object image, will be equal to the size of object, right? These are the three conditions for that. So now we will discuss about the magnification, about basically the visual angle. Now what is basically visual angle, right? Basically the angle subtended from the eye to object, that is known as visual angle. For example, this is a principal axis and this is your eye, this is your eyesight, and consider object is placed over here. So the angle between your eye and the object here, this is known as visual angle, and we will show this by alpha. This angle, this theta, is basically known as your visual angle, right? This is the angle when the object is placed quite far, like at you can say at maximum distance, like at the minimum distance of 25 centimeters, which is obviously d, right? Like which is d. But when we will when we use telescope or we use compound microscope, so it will obviously converge it and make it more clear to us, so the image will form over here, right? So the angle from this eye to the image formed, right, this angle is now increased, and this angle is basically known as beta. This is basically known as now beta. So here when the visual angle is like when the object is near, so the visual angle will be larger, right? When your object is away, then the visual angle will be is small, right? And we use this visual angle in the terms for only for telescope and for the compound microscope. Compound microscope, right? I hope this is clear to you. And like visual angle is directly proportional to the magnification. Visual angle directly proportional to magnification. Like if we'll increase the visual angle, the magnification will also be increased, right? So now let us discuss about the angular magnification, or also known as magnifying power, right? Angular magnification. Basically, it is a ratio between the angle from eye, like the angle of the ratio between visual angle of image, ratio between visual angle of image and visual angle of object, right? This is the ratio, and as we know, this magnification basically is shown by alpha upon beta. This is like, sorry, it is magnification is equal to, as I said, this is the visual angle of image, so it is beta upon alpha, right? As you can see over here, this was the object first, and this is the object after the visual angle of the object. This is the visual angle of visual angle formed by final image, right? This beta is the visual angle formed by the final image, as you can see, after the converging after the all lenses. And this alpha is basically the visual angle of the object, which is placed at a minimum distance of d. Like after d, like d is a distance, 25 centimeters a distance where we can get the maximum visual angle, because after that we can't see any object, like it will be quite blurred to us. So here beta refers to what? Beta refers to the visual angle of the final image. Visual angle of final image. And this is the visual angle of the object that is placed at the maximum or minimum distance of d, right? So here magnification is basically directly proportional to the beta. As the angle beta will increase, the magnification will also increase, but it is inversely proportional to the alpha. But as the angle between the angle which is formed by the object that is placed at the minimum distance of 25 centimeter will decrease, the magnification will obviously increase, right? So this is a relationship between the magnification and the beta and alpha. Beta is what? Beta is basically the angle which is formed from the final image, and the alpha is a visual angle of the object, right? Now let's talk about the resolving power. Basically, this resolving power depends upon the power which we have discussed in my previous video, right? It depends upon the power. Basically, it is directly proportional to the power, and we know that power is inversely proportional to the focal length. Like this is a relation that we have already known. Like as you will increase the resolving power, the power will also increase and the focal length will decrease. If the focal length is low, then the power is high and the resolving power will also be high. But if the focal length is low, then the power and the resolving both will be high. Like they are like resolving power and the power directly proportional, but the power and focal length both are inversely proportional to each other. So I hope this lecture is clear to you. If you have any kind of queries, you can ask me in the comment section. I'll be very glad to answer you guys.